Okay, then so good morning from my side. I hope you are not too tired from climbing the stairs to the seminar room, because now we will climb the Jacob's ladder of DFT. So basically continuing what Thomas told you yesterday, so from rather simple PVE-based functionals that you also had a chance to try out yesterday during the practice session, we will now basically make the functional more and more complicated by incorporating more and more terms, more and more effects. But which will, of course, increase the accuracy of the methods, but it will also increase the computational cost quite significantly. I will tell you what that actually means here during this talk. So maybe first a short recap of what you have already been told over the last 2 days and what this talk will be also based on. Okay. So of course we start from the Schrödinger equation and the Born-Oppenheimer approximation. So basically we forget about the nuclei being actually quantum mechanical particles. So we will describe them classically, and we just treat the electrons quantum mechanically. Of course that is far too complicated, which is why why people came up with other approaches such as density functional theory, and here of course only the Kohn-Sham approach. There are also orbital-free versions of that, but that's probably a topic for a whole another talk and not really widely available. The basic idea is now that we treat basically the electrons living in the effective potential of all the other electrons. And that's why, for instance, these two terms, the Hartree potential here, which is just the classical electron-electron repulsion term, and the exchange correlation term, which basically describes all the quantum mechanical stuff that we don't know about, making these two terms depending on the density, and as such as the density depends, of course, on the orbitals, making this whole a somewhat pseudo-eigenvalue equation, but for the SCF, for each SCF step, it's usually treated in a linear fashion. These orbitals need to be orthonormal, of course, to ensure that basically the wave function or the density is still somewhat normalizable and it has a defined number of electrons. Finally, we will always work in the pseudo-potential picture, meaning that we do not actually consider the electron nucleus interaction as described here, so with the classical Coulomb potential, but with more general one, ensuring that allowing us to treat the core electrons, or not to treat the electrons directly, but more indirectly via some effective potential. Okay. So what is this Jacob's ladder that I was talking about in the entrance part, so in the introductory part? So the Jacob's ladder is actually some metaphor which was introduced by Purdue almost 25 years ago, where he basically compared the search for accurate density functionals as basically coming God nearer and nearer, which is the actual metaphor in the Bible, if I read that correctly. And actually we start with the Hartree world, so we basically forget about all the quantum mechanical aspects of the electron-electron interaction, so setting the exchange correlation functional to 0. And that we basically here on Earth in the Hartree world. And then the first step to a more accurate description is the so-called local density approximation, or in short LDA, which describes the electrons locally as a homogeneous electron gas. Although that's a pretty good description for metals, it's of course not for most molecules, because there the density will change up to a certain point, especially near the nucleus, and also a bit further away when basically we are at the order of the van der Waals radius, for instance, or atomic radii of the different atoms, which is why LDA also, for instance, tends to underbind molecules. And which gave rise then to gradient approximations, where we in addition not only include the density, the local density information, but also the gradient of the density. And that was the first time that DFT became somewhat usable for chemistry. I mean, PVE is widely used, as you can see. But still, some of the effects were missing, and then people now added the kinetic energy density, and sometimes also the Laplacian of the density for even more explicit information on the system, which is then called meta-GGAs. So up to now, we are basically living in a framework which is in principle always the same. The only thing that changes is that the explicit that the energy functions became more and more complicated, and the requirements on the numerical grids that you need in order to perform these kind of operations are getting higher and higher. And that's why, for instance, the computational costs increase the more you go from rung 1 to 2 and rung 3. But still, there are a few shortcomings of that. I will talk about it also later. That's why we then start to also use the explicit information on the occupied orbitals, giving rise to hybrid functionals. That's basically like, we're blending in a little bit of wave function theory, in this case of Hartree-Fock, because Hartree-Fock has a bunch of nice properties that we would like to use, which are usually absent in common density functionals, increasing the accuracy much more, but also making it significantly more expensive. And finally, we can also include the information on all orbitals, so not only the occupied ones, but also the ones that we do not use so far, and often also the orbital energies. And that's sometimes called RPA or double hybrid functional, which I will talk about in the last part of my talk. Okay, maybe to motivate the need for hybrid and double hybrid functionals a little bit more, I show you here the accuracy of a variety of density functionals of the so-called TKN55 benchmark study, which is already 8 years old, so maybe a little bit outdated. So some functionals which were invented later are still missing. And as you also can see, the dispersion correction here is the D3. Meanwhile, we are at D4. So I guess that these values can be improved a little bit further. But what you can see is that basically from rang to rang, the mean errors decrease further and further. And especially when we go from meta-GGAs to hybrid functionals, we decrease the error by a factor of 2, which is amazing. And finally, if we then go to double hybrid functionals, then it's getting even better than that. So there's still a lot possible in order to get even more accurate results than you already had with PPE. So, but what are now the common drawbacks of those local or semi-local density functionals? Well, it's basically related to two main problems. One of them is the so-called self-interaction. The other one is the self-correlation error. Self-interaction error means that the exchange energy that you obtain from a DFT calculation does not cancel the Hartree energy in a case of a one-electron system. Because if you have a one-electron system, there is of course no electron-electron interaction. So the electron-electron interaction should be 0, but that's obviously not the case. That's not the case with most of these functionals. Another issue is that the so-called self-correlation, meaning that most correlation functionals also do not result in a correlation energy of 0 if you have a single electron system. And this leads to a variety of consequences. One of them is, for instance, that negatively charged systems are quite often unbound or severely underbound. Another aspect is that band gaps are drastically underestimated, so sometimes even to the point that systems which are actually semi-metals or isolators are predicted to be metals. And special systems like transition metals or weakly bound systems are commonly not well described or just too weakly bound. And that's why we will extend basically our local and semi-local functionals by incorporating some exchange energy from Hartree-Fock theory. So what does Hartree-Fock theory mean? Basically, as you remember, there was the Schrödinger equation, and the electronic wave function has a variety of properties, and one of them is that the electronic wave function is anti-symmetric if we exchange the coordinates of 2 electrons. And the easiest way to incorporate that into our wave function ansatz is by using a so-called Slater determinant, which is given here. So it's just a determinant of a matrix. In the rows, for instance, from row to row, we change the orbital, and from column to column, we change the electronic coordinate. And that way, everything is a determinant, but it's only non-zero if, of course, all the and this, for instance, has then this antisymmetry property as expected. The orbitals, of course, need to be orthonormal to ensure that the whole wave function is also somewhat normalizable. And if you plug that now back into the Schrödinger equation and you apply the variational principle, you arrive at which is called the Hartree-Fock equation. So the Hartree-Fock equation basically has a variety of terms. The first two are the ones that we already know from density function theory. So this H0 is basically the kinetic energy operator plus the interaction with the nuclei. This is just the Hartree energy, but written with the density. And this additional term is now called the exchange energy, which is basically the one which makes everything pretty complicated and also expensive to calculate. Quite often, as you learned yesterday, we do not work with these orbital equations directly, but with a matrix representation by basically expanding the orbitals into a set of known functions, which is sometimes just called basis set. And in CP2K, this will always be Gaussians. And what we now are left with is a determination of the orbital coefficients Ci nu. The most important part for Hartree-Fock calculations, and then also later for correlated methods, is the calculation of these electron repulsion integrals. These electron repulsion integrals are basically just some Coulombic interaction. Of course, we can also use other interaction potentials if you want to. That's, for instance, relevant for hybrid functionals. But in general, they would look as something like this here. And it has a variety of properties. Namely, it has an 8-fold symmetry, which allows us to reduce the number of relevant integrals. But nevertheless, the total number of integrals that we may need to include in our calculation still scales as with the fourth power of the number of atoms or basis functions, which is already one order of magnitude higher than common density functional calculations. But there are a few ways to bring that to reduce that further and even bring it down to linear scaling, and that's possible with one important aspect, namely the Cauchy-Schwarz bound, which holds for all mathematical norms. And this kind of electron repulsion integrals are actually some kind of norm, meaning that we can start to screen the integrals just by knowing these two simpler integrals, electron repulsion integrals, which already brings down the number of integrals to a quadratic number of relevant integrals. In addition, if we have Gaussians, we have a local basis set, meaning that these functions decay pretty fast, and that means we can also apply range-based screening just from our basis functions. And finally, if we do not consider the Coulomb potential, but I don't know, some short-range version of it, then there's also additional range-based screening possible, and that's how we can arrive actually at a linear scaling, which is also relevant for larger systems. Finally, maybe to close this up a little bit, we are dealing with periodic systems. I mean, you also, when you run your proteins, you basically have them in some kind of periodic boundary conditions, and in case of localized basis sets, to ensure that this periodicity actually holds, you have to actually sum these integrals over all image cells. And because we have 4 functions and we fix basically one to our main unit cell, we have a 3-fold sum over all image cells. And that's what makes Hartree-Fock calculations in periodic settings pretty expensive with localized basis sets. Even worse, Hartree-Fock has integrals which basically look like this. So we have basically interactions of orbitals with themselves, and these are always monopole terms in an electrostatic sense. And monopole terms have the property that the potential energy decays as 1 over r. And if you now try to add this 1 over R over all image cells, then you will see pretty easily that the sum will diverge, meaning that in a periodic setting we cannot use the pure Coulomb interaction. And that's why there are commonly two operators used instead. One of them is based on the complementary error function, and the other one is based on the so-called Heaviside function, which just says, okay, that the potential is 0 from a certain truncation radius on. And that's also the solution which is chosen in CP2K. Finally, we have to prevent double counting of the interaction potential, and that's why we have to obey the so-called minimum image convention, which means that the range of the interaction potential needs to be smaller than half of the distance to the nearest neighbor. If you have an orthorhombic cell, that's pretty easy to establish because you just need to compare basically half of the lattice parameter. Orthorhombic cell, then things will get more and more complicated. But that's the only way to ensure numerical stability of our SCF iterations. And in practice, we found that the potential operator should have a range of at least 5 angstrom, meaning that the actual cell should have dimensions of at least 10 angstrom in all 3 directions. So how do you make use of Hartree-Fock and CP2K now? So I show you the basic skeleton of a Hartree-Fock calculation in CP2K. So we have a specialized Hartree-Fock section for that. The fraction is for the ordinary Hartree-Fock calculation just 1, but for hybrid functions that will change then. You have to set up the interaction potential, and in the case of periodic systems, you need to change the potential type to truncate it because the default is always Coulomb. Then, of course, you have to set up the cutoff radius, which is to be determined by you. It should be a little bit less than half of the distance to the nearest neighbors. You have to provide some memory, which is then later used to determine how many integrals will actually fit into memory, will actually be kept into memory, and everything else will then be recalculated on the fly. And finally, there's some screening parameters. The first one is probably the more important one. And the second one is only relevant for gradients, but usually the default is already quite good. CP2K also has the option to screen to incorporate the density matrix for even more screening, but this has to be turned on actively, as if you do not start from a preconverged wave function, this will probably result in will give you wrong results. Yeah. If you run CP2K that way, you will see that Hartree-Fock will be extraordinarily expensive. And in order to reduce that, there is one approximation available in CP2K, which is basically always used, as far as I know, for simulations, which is the so-called auxiliary density matrix method. The idea is that we do not calculate the Hartree-Fock energy with the original basis set, but with a smaller basis set, smaller basis set with less, consisting of less primitive Gaussian Gaussian functions, and commonly also less diffuse basis functions. This approximation is based on this expansion here. So basically, this is the Hartree-Fock energy with the original density matrix. This is the which is the here and now. We add and subtract the exchange energy calculated from another, usually a smaller density matrix. And now we basically approximate this difference between these two exchange energies with DFT. In that way, the calculation of the Hartree-Fock term becomes much cheaper, and DFT is usually accurate enough to properly account for this difference of the density matrices. This correction function is usually PBE based. We have that available for all relevant interaction potentials that you may find also with hybrid functionals. There's a variety of projection schemes available, but the default usually works well enough. Finally, this new density matrix is not guaranteed to be idempotent, which means that basically the occupation numbers of these basically associated orbitals with the density matrix are not necessarily 0 or 1 anymore, although they used to be 0 or 1 in the original density matrix. This method now allows us basically to reduce the prefactor by something like an order of magnitude, making actually simulations on the Hartree-Fock level and also hybrid level feasible. But of course, this approximation introduces another set of parameters, namely you have to find a suitable fitting basis for this new density matrix. Fortunately, you don't have to do that yourself. CP2K comes with a large library of potential fitting basis sets for all different purposes that you may find in practice. So how do you make use of this method now in CP2K? First thing is you have to add this auxiliary density matrix method section in the DFT section. Of course, you have to set up your Hartree-Fock Hartree-Fock calculation as usual, but quite often you have to apply tighter screening parameters to have still decent convergence of your orbitals. And finally, you have to specify the auxiliary basis set using the basis set auxfit keyword in your kind sections. CP2K also provides an alternative, basically orthogonal way of reducing the computational costs, which were added more recently by using the so-called resolution of the identity approximation, which basically decomposes this rank 4 tensor of electron repulsion integrals in rank 2 and rank 3 tensors, which are basically much easier to be kept in memory. Here we have the issue that there are no pre-optimized auxiliary basis sets available, but CP2K has the option to generate these basis sets automatically using the autobasis RI-HFX keyword in the input file. Generally, all electron calculations also pretty common in other codes, especially codes targeting molecular systems. And there you can actually should be able to use the all electron, the respective basis sets in CP2K for all electron calculations if you wish. We also have a K-point implementation of that available. We have gradients available, but I will not discuss that here as it's already for the sake of time. Okay, and finally, a few words on hybrid functionals. So we've now discussed basically Hartree-Fock, but most people don't usually use Hartree-Fock because Hartree-Fock has a large, may be a somewhat good approximation, but it lacks the correlation effects, which are extremely relevant for all kinds of chemical system. And one of the basically most popular examples for that is, for instance, the fluorine molecule, which is predicted to be unbounded by Hartree-Fock, although we of course know that the fluorine molecule is actually bounded. But nevertheless, the Hartree-Fock energy is self-interaction free, which is a nice property, which is a property which is not the case for most density functionals. But density functionals already include a certain description of correlation effects. So then why not get the best of both worlds? So basically, we replace part of the DFT exchange with Hartree-Fock, which is here sometimes just called exact exchange. And then we arrive at which is called hybrid functionals, or already the rank 4 of the Jacobs ladder. Due to the variety of possible density functionals and possible interaction operators, there's a large variety of hybrid functionals available. If you just use the plain Coulomb operator on CP2K, of course, for periodic systems, the truncated Coulomb operator, you may use B3-lib, the very popular B3-lib, or also PBE0, or here as a meta-GGA-based functional, the TPSS0 functional. There are also range-separated versions available, like the HSEO6, which is pretty common for solid-state chemistry, solid-state physics, using a short range, this complementary error function that I was talking about earlier. And there's also a variety of functions based on the omega B97 approach. And these are, from my experience, actually very accurate. Depending on the level of field theories, as I've mentioned, there are also different kinds of hybrid functions available. So as with PPE0, which is based on the PPE function, which is a second rung functional, compared to TPSS0, which is based on the TPSS functional, which is on the rung 3. Just to mention that there exists the concepts of global and local hybrid functionals. In CP2K, we only have global hybrid functionals. Local hybrid functionals basically have not a global scaling factor, but a local scaling factor. But that's not available in CP2K as of now. Maybe a few more words on how to set up Hartree-Fock or hybrid calculations in CP2K. Of course, first choose your method of choice, and you have to figure out the parametrization yourself. CP2K will not look that up for you and also will not set up the respective sections for you. This includes, of course, the kind of interaction potential that you need, the scaling factors, the different DFT components. CP2K comes with a smaller variety of basic density functionals. A variety of functions which are still missing are available using the libxc library. Then you should always pre-optimize the orbitals, that you can basically apply a density-based screening for the Hartree-Fock part. Or if that's not available, just use PPE. That's usually always a good approximation for most purposes. You have to find a suitable pseudopotential. There's a variety of pseudopotentials available in CP2K. Either use the Hartree-Fock one or the hybrid ones, depending on your method. Then, of course, choose a primary basis set, and usually you want to apply the ADMM approximation. That means you also need to find a suitable fitting basis set. Commonly, a basis set of double zeta quality is already accurate enough for most purposes. Then you have to tune these 3 parameters for your calculations. So, of course, the cutoff radius is basically given by the dimensions of your cell. This Schwartz parameter is to be found by you. Usual values are the order of 10 to minus 6 to 10 to minus 10. The latter ones, especially with the ADMM approximation. Then, of course, you have to find the memory, as it vastly determines the performance of CP2K. And, if possible, turn on the screen on initial P for better screening. Usually, if you consider many hybrid functionals, the setup is a bit more elaborate, which is why I recommend you to really test this setup in advance if it's not something very simple, not a very simple functional. Generally, the Hartree-Fock code is very well not only MPI parallelized, as most of CP2K, but also excellently OpenMP parallelized, which allows you to reduce the memory demands of the code by a bit, which is relevant especially for larger systems. If you use more OpenMP threads, then you should also increase the max memory value accordingly, because the maximum memory is given as a maximum memory per MPI rank, not per CPU core. To give you a few hints on what may go wrong. So first thing is, of course, this max memory parameter that I was talking about already several times. For that, you should check the output file, where you just grab for this hfx meminfo. And then this value here, number of spherical areas calculated on the fly, should be 0. If that's not the case, you either have to increase the max memory, or if that's not possible because you're already at the limit of your machine, you should use more cores if necessary. If that's not anymore the case, then you have to deal with much significantly higher costs for the Hartree-Fock kernel. Secondly, if you use a too small cutoff radius, then this warning will pop up. And you have to figure out yourself what the correct truncation radius should be. If you have a short range potential, like in HSE06, where the parameters are basically given by the functional, you can just ignore this warning. Of course, if the convergence is bad, you try another initial guess, or maybe the thresholds are too loose, or you have to switch to another mixing scheme or change the mixing parameters. Okay, maybe how expensive are hybrid calculations with hybrid functionals? So here I show you the results on 64 water molecules, which is the standard benchmark system for us in CP2K, with a hybrid functional with the ADMM approximation. I ran this on the Pete Stein supercomputer, which was recently decommissioned, so maybe these results are not anymore up to date and could change a little bit on your machine, on your hardware. Basically, at scale out, we need something like almost 3 minutes on 8 nodes. So on 8 nodes, so one calculation is actually as a matter of minutes. Maybe with a better machine, it can be even lower. One important aspect is that the GPU usage, even with ADMM, is pretty low. The main reason is that the calculation of these electron repulsion integrals is done on the CPU, as the library that we employ for that does not offload to GPU. But there's current work in progress to fix that issue. Okay, after talking about hybrid functionals, so why do we still need even more if the accuracy is already much better than with semi-local functionals? Well, basically, we still lack a description in Hartree-Fock. And most hybrid functionals based on DFT, they have only a local description of correlation, ensuring that, causing basically that the interaction energy is of uncharged particles with basically no dipole moment and even no quadrupole moment decay exponentially fast, which is not how it's supposed to be according to London, who predicted for van der Waals interactions a decay of 1 over r to the power of 6, which is why we require dispersion corrections. And that's why people started to consider correlated methods. So basically, what we now try is capturing the actual correlation effects which are predicted by the Schrödinger equation. There is a large variety of frameworks available. The one which are relevant for CP2K are the MP2 method and the RPA method. There are also a few others than just wave function based, so like MP2 or couple cluster, which you may be familiar with, and also many-body perturbation theory, which are, for instance, like the density matrix renormalization group or the quantum Monte Carlo method. These are not available in CP2K, but are probably the most accurate methods that we know of, but not vastly available. They are purely ab initio, meaning that there are no empirical parameters included, and they can also be improved systematically, which is pretty important if you want to improve your results for whatever reason and to have the computational capacity to actually do that. And the dispersion interactions, which are also relevant for biochemical systems, are basically a byproduct of this whole procedure. I will start with the MP2 method, with the description of the MP2 method, as it's also the method which was implemented first in CP2K. MP2 is based on perturbation theory. On perturbation theory, and basically looks like this. Doesn't look too dangerous for now, but if you check out the equation a bit more deeply, so you will see it's basically a sum of some electron repulsion integral with this T, which is some kind of transition amplitude, which again depends on electron repulsion integrals. So we again have to bother with electron repulsion integrals. The electron repulsion integrals are now here given using molecular orbitals and are usually obtained from the ones in the atomic orbital base by successively multiplying with the orbital coefficients. Because of this step, this whole procedure scales with the 5th power of the number of atoms, so it's even more expensive than Hartree-Fock. Another problem is that way you always have to store one of the, at least as intermediates, some electron repulsion integral, which requires you to store basically a huge number of integrals. So for 64 water molecules, it would be at the order of terabytes. And that's basically unacceptable for even larger systems. That's why in CP2K we have the so-called resolution of the identity approach available, which basically works similar to the one in Hartree-Fock. And this allows us basically to decompose this tensor of rank 4 to a tensor of rank 3. And this tensor of rank 3 can now be stored in memory. For 64 water molecules, for instance, the storage of this tensor takes about 50 to 60 gigabytes, so that's feasible for most high-performance devices. It not only reduces the memory footprint, but it also reduces the computational cost by order of factor of 20 or so, depending on the system. And that's what actually makes MP2 calculations also feasible for larger crystals. But still, the calculation of these 2 electron integrals here is dominating the computational costs. So how do we actually calculate these integrals? Well, again, you see the GPW method that Thomas was talking about yesterday, meaning that we basically start from these auxiliary basis functions that we introduced to expand our densities, calculate the potential using our GPW approach, transform it back, integrate the potential, and that's also how we can run these operations on the GPU, making it significantly more efficient. That way we can also take care of lattice sums, but we are, of course, now restricted to pseudopotential calculations. But as these calculations are expensive anyways, we want to reduce the computational cost as much as possible, which is why it's a suitable approximation here. And in contrast to Hartree-Fock, we can actually use the Coulomb operator, meaning that we have basically less errors in that regard than in contrast to Hartree-Fock. So the actual implementation is a little bit more elaborate. To cut a long story short, and for the sake of time, for the sake of time, we basically distribute, we calculate the integrals batch-wise, contract everything using local matrix-matrix multiplications, using matrix multiplications. There are several ways to accelerate it, to basically reduce the communication costs and allow a little bit more parallelization to basically also make use of the memory that we have available, as these operations are generally rather expensive, significantly more expensive than the actual memory demands. In order to set up such an MP2 calculation, we have a new section, which is the wave function correlation section, as shown here. This number of process basically is used in several occasions. It should be kept at 1 if possible, but for larger systems it may be necessary to increase that to prevent running out of memory. As we have a GPW-based approach, you of course have to optimize another cutoff, but from my experience, the cutoff of fusion is already accurate enough for most systems. If you are a bit paranoid, you can also go up to 300, but more is actually not necessary here. And finally, you have to activate the RI-MP2 section. We have that also for the other correlation methods, where you have to activate the respective other section. Another thing is that you will need special basis sets. Here I showed you the basis RI-CCTZ. There's also a more modern one, which gives you suitable basis sets for the whole periodic table, not only for the elements relevant for organic or biochemistry. Of course, you should start from a pre-converged calculation, as with Hartree-Fock. Then finally, you need to specify some auxiliary basis set. In case of the basis RI-CCTZ, there are also suitable pre-optimized basis sets available in this file. So how do you generally set up such a calculation? Of course, you need to pre-optimize the orbitals, as already mentioned, with a respective hybrid function or Hartree-Fock. You need to optimize the parameters, and most relevant here is the cutoff, of course. And there are a variety of parameters to tune, which is what I recommend you to do if you are interested in large-scale calculations, not only just 2 or 3, but let's say thousands. So after we have been talking about energy calculations, of course, you not only want energies, you want gradients. I mean, you want to run some kind of simulations. CP2K employs something which is called a Lagrangian ansatz, meaning that we basically augment our energy functional with the equations to ensure that the orbital energies are still basically the diagonal elements of the Fock matrix, and the second one is that the orbitals are still orthonormalized. If you basically do the maths about it, then you will find that you need to solve something which is called coupled perturbed SCF equations. That's these equations are solved in principle a set of linear equations, but because of the sheer number of them, so at the order of millions, even for smaller systems, these are solved numerically. These equations are basically as expensive as an ordinary SCF equations, as you also have to apply, for instance, the Hartree-Fock operator, which can make these kind of calculations even quite expensive for certain systems. In general, such a gradient calculation is 2 to 3 times as expensive as an energy only one, and is especially costly if you're interested in stress tensors, for instance, with barostats, if you want to run your calculations with some kind of NPT ensemble, for instance. In general, the Hartree-Fock part is in principle should be cheaper for larger systems, but for medium-sized systems, as at the order of 64 water molecules, then it is still recommended to apply the ADMM approximation, because otherwise this operation is still far too expensive. I won't dive through all the equations, that's just for you later. So the basic idea is that any kind of gradient that you want from this Lagrangian is just this given by this expression, no matter the actual perturbation. The perturbation can be, for instance, an external electric field. Then you arrive at, for instance, the dipole moment. It can be nuclear coordinates. Then you arrive at nuclear gradients. Or it can also be the parameters of the components of the cell vectors to give you the stress tensor, for instance. These equations are basically the same. You also used by the other methods. I will show you in a few minutes. So there's really a lot of maths included, but usually the actual implementation is actually for MP2 is still rather simple. One thing to mention, maybe if you have very localized orbitals. So for instance, when I try to run argon, which is very localized, and the orbitals do not change a lot, then for numerical reasons you have to switch to another formalism which uses the so-called Lagrangian matrix, which is given. You cannot use. So usually you can use some kind of shortcut, which is given here for MP2. But in certain cases, as with, of course, the diagonal elements or some orbitals which are very similar in energy, then this expression here becomes numerically unusable, and that's why you have to basically use the explicit formulation, which is this sum, which is basically given by these expressions here, which are rather expensive to calculate. Okay. Maybe a few words on how to set up the gradient calculations. Of course, you start with a setup for the energy calculation, but in addition, you can, of course, configure the calculations of the gradients. And for that, CP2K has an additional section, the canonical gradient section. You don't have to set it explicitly. It's just if you need to adjust the parameters. One aspect is, for instance, that this free HFX buffer, which allows it to reduce the memory demands by basically freeing all the Hartree-Fock buffers, sometimes fails, and that's why you usually set it to false, but if you can, you should set it to true to save some more memory. And finally, this abs.conf basically determines the accuracy of the solution of these coupled perturbed SCF equations. Of these coupled perturbed SCF equations, and that's of course the one which determines finally the accuracy of your gradients, whatever kind they are. Maybe some pros and cons of RI, MP2, and CP2K. So generally, it's of course more accurate than hybrid functionals and also many density functionals. not necessarily hybrid functionals, by the way. And it has a version which is probably pretty relevant, which can be relevant to you. But in general, MP2 is of course much more expensive than Hartree-Fock, scaling with a fifth power of the number of atoms. There are a few systems which cannot be described, namely metals, as then basically the orbital energies turn to zero, and quite often short-range effects are also not well described. That's related to the lower order of perturbation theory. And in case of RI MP2, you cannot use all electron calculations, but I think that's probably something you don't want to do either. Okay. One issue is that we have with RI MP2 is this extraordinarily steep scaling, and in the literature there are a few methods available which are much cheaper than that. And one of the first which was introduced more than 15 years ago is the so-called scaled opposite spin MP2. This is obtained from MP2 by basically neglecting some of the components, which making these operations expensive. But it allows us to basically reformulate the whole theory into this integral here. This integral is a trace of a square of this matrix-valued function Q. And this Q now is given by this multiplication here, or this contraction. And this contraction now has the favorable advantage that it's not scaling with a fifth power, but with a fourth power. So it's definitely cheaper than ordinary MP2. This integration is of course not performed analytically, because that would be equivalent to determining the MP2 energy as we did it before. But instead we perform it numerically, and with the so-called minimax quadrature rules, we need something like 6 to 8 quadrature points for decent accuracy. A similar approach, which is meanwhile pretty popular in the quantum chemistry department, is the so-called random phase approximation. The random phase approximation has a pretty long history, as you can see with the number of literature that I provide you here on the slide. But the formalism that we use for our RPA implementation is based on which is called adiabatic connection fluctuation dissipation theorem with a certain approximation. And if you compare the RPA equations with the SOS MP2 ones, you see they're structurally very similar. It's just that you have a different prefactor here, you have a different function that you apply to the matrix, and you have a different kernel that you have to multiply here. But generally, it's basically the same, which also makes the implementation of both methods very similar to each other. This integration can be performed in two different ways. The more expensive, but also more general one is the Clancher-Curtis one. That's, for instance, also the one which is used for GW calculation for band structure calculations. But we also have minimax quadratures available, which are as cheap as the one used for SOS MP2. We also, the random phase approximation is quite often applied in the following way. Basically, you run, for instance, a PBE calculation, then you remove the exchange correlation contributions from PBE and replace them with exact exchange, so Hartree-Fock, and this correlation energy from RPA, and that's a very good which provides already with a pretty good description of your system. Unfortunately, RPA has a variety of flaws, which is why there's also a variety of corrections of post-RPA or beyond RPA methods available, which are given here, but unfortunately we do not have gradients for that if you are interested in them. So how do you set up these kind of calculations now? Well, it's basically pretty similar to the MP2 calculations. You basically just need to replace the RI MP2 section with the respective IR-RPA or ISOS MP2 sections. And as I've mentioned, we have some kind of numerical quadrature. And That's why you should already have to set this number of quadrature points explicitly. My recommendation is that it's somewhat a divisor of the number of processes that you use to run the calculations, because then CP2K can basically distribute all of these quadrature points to different subgroups, which are each responsible for a certain subset of these quadrature points. If you think you are more clever than the automatic, than the automatic or than the default way path in CP2K, you can also set the number of these integration groups, which basically are each responsible for a set of quadrature points, explicitly. Performance-wise, the calculation of these Q matrices is implemented using parallel matrix multiplications, or the PDGEM routine of the P+ library. This is excellent for GPUs because matrix multiplications are then extremely fast, but it requires a suitable implementation of this function here. As far as I know, the standard ScalaPack implementations do not provide that, but I know, for instance, that Cray machines quite often have the library which is called libsci-ACC, which basically has a GPU variant of the PDGEM routine. If you do not have that available, but have a computer with GPUs available, then you can also use the Cosmo library instead, which is actually the preferred library in this case because it not only offloads the operations to the GPU, but it can also reduce the communication costs, which is pretty useful. In case of RPA, there are a few more keywords. One of them is the minimax keyword, which you should always set if you are not only interested in GW. The exact exchange calculation is configured with a separate Hartree-Fock section in the RI-RPA section. It's basically set up as every other Hartree-Fock calculation. But my recommendation is here that you set the max memory to 0 because you will usually not reuse the integrals later. Finally, as already with MP2, the Hartree-Fock calculation can be pretty expensive, which is why there's still the need for the ADMM approximation in this case. There are, of course, also some beyond RPA's corrections, but I think it's not really necessary for you as you will be in need of gradients anyways. Okay. Speaking of gradients, the basic approach is similar to the implementation of gradients with MP2, and the general setup is also pretty similar to RI MP2. In CP2K, we fix the quadrature rule. Generally, it's also significantly more expensive than RI MP2, especially for larger systems. But it's not suitable for very large systems. If you're interested in that, we have a low scaling implementation available, which should be more suitable for that purpose. But I think it should be too expensive if you're really interested in simulations, not just single static calculations. These are just the equations. Are a little bit more complicated now because we had this integral, and that also makes the implementation a little bit more complicated. I won't dive too much into that. Here maybe some small application of my gradient implementation where I considered the benzene crystal. So benzene has a variety of polymorphs, and in the literature it's not yet quite clear which one is the more stable one. And as far as I know, there's a variety of possible polymorphs, and the actual energetical order of them is still not known until today. The main reason for that is that the relative energies are really pretty small, so in the order of 0.1 millihartry or 0.1 kilocalorie per mole. And I used some additive scheme for two benzene dimers, and then in order to estimate the cohesive energy and also the relative energy between both methods, between both polymorphs. And what we can see is that we are already pretty close to the experimental results in the case of the cohesive energy of the benzene crystal, especially if we consider post-RPA methods. to correct for some of the flows of RPA. The relative energies here is at the order of 0, which is basically the correct one, but of course nobody really knows what's basically the experimental value for the relative energies of polymorphs, as that also depends on the 0 point order energy corrections, which I was able to estimate here on the RPA level, but with a rather small unit cell. So basically these numbers here are more like some idea on what the correct value is, but probably it will be a bit different from that. Okay. As with hybrid functionals, we can also, where we mixed DFT exchange and Hartree-Fock exchange, we can also do the same for the correlation part. And the general idea is actually that most correlated methods in Hartree-Fock, they describe the long-range behavior pretty well, but usually not the short-range behavior, because we are commonly bound to lower orders of theory, whereas DFT easily describes the short-range behavior of our system, but not really well the long-range effects. And then, as with hybrid functionals, we not only mix the DFT exchange contributions, but also the DFT and then MP2SS and MP2R RPA correlation contributions. So basically, the double hybrid is the best of both worlds that we can do for now. The flavors, there are, of course, again, as with hybrid functionals, different flavors of double hybrid functionals. Of course, depending on the underlying DFT functional, the underlying exchange part, the underlying correlation part, so the different, so whether it is range separated or not, whether what kind of correlated methods we use, and of course whether you fit all the different parameters now to some theoretical constraints or to match the experimental data. In general, they are much more accurate than the underlying methods, as I've already shown you with the GM-TK and 55 benchmark from the beginning. But I also run a few benchmarks, and I think I also have 1 or 2 slides on that in a few seconds. Maybe some more words on how to set up double hybrid functionals in CP2K. So it's basically similar to the hybrid functionals, but of course now with even more sections to set up. So it's not only the DFT functionals or not only the Hartree-Fock part, but it's also the wave function correlation section with the respective scaling parameters that you will need here. In addition, there's also the interaction potential section to set up basically range-separated double hybrid functionals, because the default is here again the Coulomb potential. Regarding pseudopotentials, I have good experience with the ones optimized for hybrid functionals, but I haven't tried transition metals yet, where the situation might be a little bit different, because double hybrid functionals usually employ a higher ratio of Hartree-Fock exchange, so of around 50% than just the ordinary 20 to 25% of hybrid functionals. That's why I really recommend you to check the correctness of your setup, so whether you really have the correct parameters, but also whether it gives the correct results. For some inspiration, we have a few double hybrid functionals predefined in the data directory, where you also find the basis sets. Gradients are fully supported, are also fully supported for all kinds of double hybrid functionals. Finally, last few words on the basis sets which were also discussed by Thomas yesterday. So in general, for correlated methods, they have the disadvantage that they converge really slowly with respect to the size of the basis sets. But the general guide, it is known that you need a very high angular momentum quantum number. So not just like d orbitals if you have p-block elements, but quite often even f, or for larger basis sets even g orbitals for accurate numbers. That's why there are the so-called correlation consistent or CC basis sets. Because of the GPW approach, we have certain restrictions on the exponents there, and that's why CP2K has its own basis sets available for this purpose. The basis RI CCTZ are the older ones, but are well tested, but cover only a few main group elements, mostly relevant for organic and biochemistry. Whereas the basis CCGRB UZH are the more recent ones, and basically form a consistent set of basis functions for the whole periodic table. So if you're, for instance, interested in transition metal chemistry of your enzyme, then these are the basis sets to use for that purpose. The RI basis sets are a bit more tricky because we only have them for the basis sets in the basis RI-CCTZ file, whereas for the other basis sets we have only two options. One of them is that you let CP2K generate them automatically. This means that they're usually not too well optimized and are quite often even a bit larger than the ones you have in the other file. Which is why I recommend you, if you are interested in using these correlated methods with the new basis functions, then you should optimize some of them yourself. If you need some help, there are a few hints on that in this directory of our regression tests. My recommendation is that in contrast to ordinary density functionals, where a double zeta basis set was already sufficient, you should employ at least a triple zeta quality basis set for correlated methods, or if that's not feasible, maybe an augmented double zeta basis set for somewhat converged results. Okay, finally, a few words on the accuracy of double hybrid functionals in condensed matter, not only molecules. I have here the errors of the cohesive energies of some molecular crystals, so neon, argon, ammonia, and hydrogen cyanide. And as you can see, the PBE has a somewhat decent accuracy for all of these systems. RPA and MP2, interestingly, always on the same level, which is basically related to the missing short-range effects. But if we now go to, for instance, the PW-RB95, which is an RPA-based double hybrid functional, or the Omega B97X2, which is a MP2-based double hybrid functional, they are significantly more accurate than most of the other functionals. Then a few words on the application of the ADMM approximation, because which is still relevant for double hybrid functions, although they are already pretty expensive. I show you here the errors that you introduce to double hybrid functionals in some energy differences and the analytical gradients. And the errors, I think, are pretty acceptable. If you think that's too large, you can still increase the fitting basis for the ADMM approximation. A few words on the performance, why we actually need it. So here I show you the computational timings of a double hybrid functional for a variety of systems. And if you employ something like a double zeta basis set, which is, as I've told you, not my recommendation, then usually there is not really an acceleration. But in case of argon, where we have to employ augmented basis sets for accurate results, you already observe an improvement in the factor of 2 of the total timing, not just the Hartree-Fock part. So that really means that the Hartree-Fock calculation or Hartree-Fock part of such a double hybrid functional calculation is definitely still somewhat driven by the Hartree-Fock, or it still really depends on the Hartree-Fock performance. But if we go to a larger basis set, so a triple zeta one that I would recommend you to use, then you will always observe an acceleration using the ADMM approximation. Maybe finally, is how expensive is such a calculation? Of course, it's significantly more expensive. So with the hybrid functional, we went up to 16 nodes. So we basically started here. And we had the order of 20 or 30 times more expensive than with a hybrid functional. Of course, with a larger system, that may be a bit different. But and on the other hand, the computer that I was using was again the Pete Stein supercomputer. So the numbers are a little bit outdated, but I think should be still similar than with modern computers to modern computers. If we are at scale out, the chip usage drops down to 28%, mostly because of communication and the Hartree-Fock part. Okay, with that, I'm at the end. And we can summarize that CP2K can do these kind of calculations, so basically of all rank of the Jacob's ladder, and also for different kinds of periodicity. So here I have only shown you three-dimensional periodic systems, but you can also, of course, run these calculations for gas phase molecules if necessary. The auxiliary density matrix method is pretty important for performance, not only for the Hartree-Fock or hybrid calculations, but also for double hybrid calculations. Systems with a few hundred atoms are feasible, and for hybrid functions, I can tell you that there are also a variety of studies available using hybrid functionals in actual dynamic simulations. Double hybrid functionals are fully supported. It's really important. It's pretty performant, well parallelized, but the libraries are important. So for Hartree-Fock, it's the Libent library, but maybe we can replace it in the near future. Whereas we have two other libraries for the MP2 or the RPA part. All electron calculations, if you are in need of that, are not too well supported. Metallic systems can currently also not supported if you need that. And it's suitable, for instance, if you calculate training data, for instance, for machine learning potential. That's something that I have already done, but I don't have the results yet because that's done by my collaborator. And you can also use these methods basically as some kind of subsystem, using some kind of subsystem embedding that I haven't shown you here. I'm currently working on, so there's currently some work in progress on the GPU acceleration of the Hartree-Fock kernel, which should make it even hopefully much faster on GPU-based hardware. And also, I'm currently working on finite temperature effects in RPA such that you can even treat metals with a correlated method. Okay. That's it. If you have questions, I'm happy to ask them, to answer them.
So thanks for the wonderful talk. If I'm performing, let's say, hybrid DFT calculations, does RI offer more advantages beyond what ADMM is doing?
Well, in principle, both ADMM and RI Hartree-Fock are orthogonal methods, so you can basically use both of them together. Although I don't have too much experience with that, so I don't have much experience with RI RPA, as it's more recent, as it was implemented more recently. I do have some experience with ADMM, of course. An issue may occur if you have very large systems, because RI RPA is always cubically scaling in that point, whereas the ordinary gamma point implementation, so without RI, then goes down to linear scaling.
So the ADMM bases, you use them when you have fully or part of Hartree-Fock, but the CC bases, can you also use them with PBE, or is that?
You can also use them with PBE, of course. Yes, these are just ordinary basis sets. And as far as I know, they were even optimized using PBE.
Okay.
Maybe I ask a question. So you talked about those methods beyond traditional GGA DFT. Mm-hmm. For example, hybrid DFT, MP2, and RPA. And also you present some, let's say, benchmarking for bulk water, I think, and benzene. Do you have some, let's say, some perspective or recommendations for users, so that one user can think about using this method for their particular interesting system? Yeah.
I think it depends a bit on the system. So if you have, I don't know, very simple, so if it's, I mean, one thing is that you have, of course, also dispersion interactions available. I mean, these are pretty important if you have interactions between molecules. If your semi-local function, or like PBE already provides a decent description of the electronic properties, then the standard empirical dispersion correction should be acceptable. If it's not anymore the case, because you have, for instance, transition metals or charged systems, especially anionic systems, then you should include Hartree-Fock and go to hybrid functionals. If you really need high accuracy, because the electronics is still not that well described even by a hybrid functional, because maybe also the self-interaction is still too large, then you should go up to either to a special hybrid functional or to a double hybrid functional.
Okay, so again, when performing hybrid calculations, in your experience, is there a general recommendation, like with the parallelization, like running on the OpenMP, MPI, hybrid?
So from my experience, so I usually can run, I think my systems are just too small, then you can run everything on using basically 1 or 2 OpenMP threads per MPI rank. I think if the system becomes pretty large, then you have to imagine that for the implementation in CP2K, the density matrix and the Fock matrix are replicated over all MPI ranks. And that's basically the computational bottleneck here, because if you cannot keep 1 copy of it on each compute node, then of course the Hartree-Fock implementation is not anymore of use. So then you really have to use something like RI-Hartree-Fock. If you're basically in that regime where 1 MPI rank cannot store 1 copy of the matrices anymore, then you should increase the number of OpenMP threads and reduce the number of MPI ranks per node. But I mean, that's something that you will then see sooner or later when you have an out-of-memory event.
So I guess, thank you. Again.